Welcome to video 3.3. In this video, I'll be covering the 20 amino acids, covering their structures, pKa's, and other important features to memorize and know about them. While this video will be covering all of the material, I highly recommend that you make flashcards and rote memorize the structures of these amino acids and the charges they can take. There's a lot of pattern recognition here, and where lots of this course is memorizable, so to speak, there's a lot of understanding to be had. For this section, understanding is really going to have a requirement that you do know these structures and you know the charges they make. So again, highly recommended here that you seek to memorize your R groups for all 20 amino acids, as well as their associated structures and pKa's. So without further ado, again, the amino acid has an R group at the alpha carbon, and changing that R group is what changes the amino acid. So you're always going to see this backbone. Now let's take a look at how we can group the amino acids. In total, there are 3 key groups I want you to be paying attention to. There are 8 hydrophobic, otherwise called aliphatic amino acids. There are 8 polar amino acids. I'll call them polar uncharged. And there are 4 charged amino acids. So in total, we have 20. Now, the hydrophobic amino acids, or the aliphatic, these are generally going to have lots of carbon and hydrogen. And it's not saying that they won't have other, oxygen or nitrogen atoms, but generally we're not going to be seeing strong dipoles. We're not going to be seeing any H bonding. With the polar amino acids, we're going to see that all of them have some sort of polar group for the most part. And of note, some of them have pKa's, which means that some of them are therefore ionizable. Right? Not all of them in this group, but some of them will be able to actually take on a charge. Some of them are neutral at pH 7, others aren't. We'll go through it. But the reason why we call this last group charged, I like to separate them, or ionic, is that they all have a pKa. So all 4 of these amino acids in this charged group are charged. We call them charged because at pH 7, they are fully charged, right? They could be fully negative, fully positive, where with polar compounds, it might be, it's more of a mixed bag. The charged ones are always charged at pH 7. Right? Biological conditions, we can imagine them as almost always being charged. Now, without further ado, let's start talking about the first group. I've organized this into a table format. Keep in mind that the structure that I draw in this column is directly connected to the alpha carbon. So there's no extra carbons. Assume that red squiggly connects us. Now, every amino acid also has a 3-letter code associated with it, and it's highly recommended that you commit those to memory as well. For alanine, the 3-letter code is ALA, A-L-A, and if you need to know the 1-letter code for whatever reason, the 1-letter code is A. So the structure of alanine, super simple, and most of these hydrophobic amino acids aren't so bad. The only thing connected to the alpha carbon is 1 extra carbon, a methyl group. So that's it. That's alanine. If this is a methyl group, we call this amino acid alanine. Key feature is that it's small and it's hydrophobic. Right? There's really not much else to consider with alanine. It's pretty boring. And considering, that we need to memorize them, we like having some boring ones. Moving next to leucine, its 3-letter code is LEU, and its 1-letter code is simply L. Leucine is a little bit more elaborated than alanine. We're going to have a carbon off the alpha carbon. Then we're going to have what's called, so if we count the number of carbons here, 1, 2, 3, 4. 4 carbons, so this is actually a butyl group. And in chemistry, we actually call this a sec-butyl group because the last carbon, or actually not sec-butyl, sorry, isobutyl. And I like to view that as the last carbon splits equally. Iso is same, so they're same on both sides. It's like a fork. So again, just another carbon chain of 1, 2, 3, 4 carbons, right? It's larger, but it's the same kind of hydrophobic. There's nothing really going on there. There's no hydrogen bonding. The only forces involved are London dispersion forces. It's just bigger. Continuing on with this trend, valine is much the same. Valine is nice because you can just say V for valine, and it's shaped like a V. If we take that again, connected to the alpha carbon, it's like the leucine, except we're missing a carbon. So it's just 3 carbons directly attached and makes a V shape. It's a little smaller than alanine. It's a little bigger than leucine. Again, there's not much to say here for key features. It's just different sized carbon chains. So now we'll get the last of the kind of branched chain amino acids here, isoleucine. You'll notice it'll be very similar to leucine. Its 3-letter code is ILE, and isoleucine's 1-letter code is I. So isoleucine is quite similar, except this is going to be the sec-butyl group. So we still have 4 carbons, except they're attached a little bit differently. Right? That first carbon is connected to 2 different things. That's why we call it sec in chemistry, where you can see how isobutyl is still 4 carbons, but they're shaped a little bit differently. Very similar to leucine, just a different shape. Nothing remarkable about it. So far, you can really see how all of these structures are hydrophobic and don't have much going on. Now with methionine, we'll keep it going. The 3-letter code is met, and the 1-letter code is M. Right? Nothing too crazy. We're going to see the first atom that isn't carbon here. So we have 1, 2 carbons, followed by a sulfur, and then 1 extra carbon. So this extra carbon here is just going to be a methyl group, and that ends the molecule. There is some polarity here, since sulfur is a little bit more electronegative than carbon, but all in all, we don't really consider this polar. It's still a non-polar molecule. So it's methionine is nice because there's a methyl group at the end, but at the end of the methyl kind of makes sense that way. But also just keep in mind it's the only one like this where sulfur is in the middle. So its unique feature is sulfur in the chain. Right? Importantly, there is no SH bond. Right? This is kind of in the middle, it's not at the end, which we'll come to in a second, or in the next section. Cool. Phenylalanine. So phenylalanine is a pretty big mouthful, but its 3-letter code is PHE, and its 1-letter code is F. So this is the first time that the 1-letter codes aren't just simple. There are going to be some distinctions. If you're taking the MCAT, for example, you will need to know the 1-letter codes, and some courses may require it as well. Just include it in your flashcards or not, depending on what you need to know. For phenylalanine, we're going to be connected. So it's alanine, right? Like alanine up here, just 1 carbon. We still have 1 carbon, except connected to that 1 carbon is a phenyl group. Phenyl means benzene. So we have a 6-membered ring, a big ring here. This is phenylalanine, and all you need to know about it is that it is, large and in charge, I guess, but really large and nonpolar. It's one of the larger amino acids. You can see how big a benzene ring is with all those extra carbons. So again, so far, this hydrophobic family all have not much to say in that other column. Tryptophan, this is where we're going to start getting some very interesting side chains. Its 1-letter code is W, which you can memorize. I like to say tryptophan and then just put the W in the name. But the 3-letter code is more sensible. It's TRP for tryptophan. Now, drawing tryptophan from memory isn't something I'd necessarily recommend unless you are told you needed to, but it looks something like this, with a 5-membered ring connected to a 6-membered ring of benzene, like so. This, I believe, is called an indole ring. That's the name of the chemical. But long story short is it's a very bulky. It's actually connected, I should say, by 1 extra carbon to the carbon. So there's 1 carbon followed by this big ring. And this is actually the amino acid in turkey that makes you sleepy. But again, it's large. And you'll notice while there is a nitrogen that could be considered polar, there is some H bonding that can be done here. Right? We have a lone pair now. We have a hydrogen. It's so large that we still generally consider it large and hydrophobic. But if you are asked if this can do H bonding, the answer is it can. Right? And last but not least, proline is sometimes put in a different category. I'll put it in this one. Or actually, so I'll put it in this one. Now, proline is quite interesting because it's the one amino acid where, if we look at the let me draw the full structure. So if we have our C terminus, and we have our N terminus. Typically what happens is there's an R group connected here. The interesting thing with proline is that the nitrogen is actually going to be part of the R group. So it can still be connected to something else in the sequence, but proline is actually involved at not only the alpha carbon, but is also connected to its nitrogen. So it makes this nice 5-membered ring. It's a very different amino acid than usual. Keep in mind that usually things are only connected to the alpha carbon, where here it's actually connected to its amine as well. This is, we consider it, non-polar because it's got only carbon. But importantly, it's very rigid. And this will come up later when we talk about protein secondary structure. But proline, it's very, compared to other amino acids, it just really throws a knot into things. It's very rigid, and it's a ring, so rings don't like to rotate very much. That's what you need to know about proline, right? Its 3-letter code is PRO, and its 1-letter code is P. So sometimes it's considered a special case, but since it's fairly nonpolar and it just has carbons, I like to put it in this camp. So if you want to take a quick look and screenshot, these are the 8 hydrophobic amino acids. This will be a long video as we continue to go down, so feel free to go back and screenshot that if you'd like to put it in your own notes. Now let's talk about the 8 polar amino acids. These amino acids are going to be, again, 8 more of them, but they're polar and they have side chains that are generally ionizable. They can be ionizable, rather. So serine is a 3-letter code SER, 1-letter code is S, and connected again to the alpha carbon. With serine, we're going to see a carbon connected to an OH. And you can see why this is a polar amino acid. It's similar to alanine in size, right? It's got this extra OH, which means it has 2 places it can do H bond accepting and 1 H bond donor, right? This means it's going to have favorable interactions with water, like all of the other polar amino acids will. So key feature is it has H bonding. And I guess it's fairly small compared to the others. Threonine is THR. Its 3-letter code, right, is going to be, or is, THR. Its 1-letter code is T. And what happens here is, and this can be kind of difficult to draw, but I like to view it as threonine means you're connected to 3 different things. Threonine. So we have our carbon, and that carbon is connected to 3 different things. A methyl group, an OH, and a hydrogen. That's how I like to view it. 3 distinct different things. Drawing it normally, since we don't typically draw in hydrogens, it would just be a methyl group and an OH. Right? But keep in mind, there are 3 things: the carbon, the hydrogen hiding in the background, and the OH. So threonine, very similar to serine, it's just a little bit bigger. Right? And these are the different tools that our cells get to play with when making proteins. So key feature is very similar to serine. Now we're going to start getting into some interesting structures. So cysteine. If you recall, back in the nonpolar amino acids, we had a place where sulfur showed up. Remember that sulfur shows up in proteins in the R groups. And here, methionine had a sulfur in the middle. So it was nonpolar. It doesn't really do anything to care about. Maybe some H bonding. But here with cysteine, CYS, or C, we actually have a carbon, right? So we have 1 carbon, and then we're going to have another carbon. I'm just making, no, not another carbon, just 1 carbon and the SH. So it's kind of like serine. It's very similar, except it has a sulfur. Now, what makes this different is that this is on the end. It's terminal, which means there's an H there. It allows for more H bonding, but more importantly, right, really importantly, is that it is ionizable. And so you'll see as the first ionizable amino acid, I'll be including all the pKa's here. So cysteine, with its ionizable pKa of around 10.5. And again, the numbers you're given in your own course, if you're at the U of A, you might give, these numbers can actually vary depending on different proteins, all these things. You'll be given a value in your course if you're taking this biochemistry course. So make sure you use the values that were given. These are just approximate. So with a value of 10, or let's just say 10, let's keep it simple. Right? What that means is that this, essentially, we have sulfur, and when the pH is lower than 10, so if we think about pH 7, right? Actually, I think it's pKa 8.5. Give me a second. Let me just pull up a reference. Of course, I highly recommend you have these memorized, but this will be handy for me. So yeah, if we're looking at cysteine, and so I see this pulled up as the side chain is 8.4. Yeah, so there we go. 8.5 is a better number for cysteine. What that means is at pH 7, if we think about this from last video, a lower pH means less or means more hydrogen, and that means that the HA form, SH, will dominate. However, when the pKa, right, when the pH hits 8.5, now we're going to start seeing a lot of the A- form, right, which is sulfur with a negative charge. And this is really involved in something called disulfide bonds, we'll talk about later. Keep in mind that you want to know the pKa and the two forms of any ionizable amino acid. So in this case, it's SH is the HA form, neutral, and the A form is S-. We don't see any positive charges with cysteine. Okay, let's keep it going. Tyrosine is TYR. Now, since T is taken by threonine, we use Y for this. This is another amino acid that's quite large, so some people consider it hydrophobic. But there's an OH at the end, so again, we have hydrogen bonding that OH can allow for. Now, looking at my reference document here, we see that tyrosine has a pKa of about 10.5, so that was what I was thinking of above. 10.5. Similar, it's ionizable. So this is the HA form. So the HA form has, I'm just going to draw the ring version, OH, and the A- form, where you have the benzene ring, and there's an O-, right? So once again, while this is still hard, right, your pH has to be 10.5 to start seeing this, or to have a 50-50 mixture when they're equal. Point is that it's still reasonable that you can deprotonate this and get a charge on tyrosine. So once again, it's worth noting. Okay, histidine is a really cool one we're going to be talking a lot more about in the next section. Its three-letter code is his, and we have a capital H. Now, when it comes to drawing histidine, it can be more of a challenge. But what we'll see here is we have a carbon. It's connected to a 5-membered ring. So there's a double bond N, double bond N, like so. So here's histidine. Now, again, the structure, I guess this one, depends on your course. I'd recommend you memorize how to draw it. The important idea is that, remember this lone pair. This lone pair is not accessible for H bonding, but this one is, since it's got that nitrogen double bond. Histidine is also ionizable. Right? Histidine has a pKa of around 6. And what that means is, and I'm just going to not draw the full structure here, but we can have the neutral version of histidine. So the A form is the neutral version. And if there's an extra hydrogen, histidine can actually become positive. That would go here on this nitrogen. Right? So now we'd have a positive histidine, and that can actually happen at pHs that are very close to 7. Right? The closer you are to 7, the more relevant the ionizability of the amino acid is, because it's more realistic to actually see those charges. So keep in mind here that while in these forms HA was neutral and didn't have a charge, histidine is actually positive with a neutral, it's positive when it's in its HA form. So keep in mind that difference. Having those things memorized will save you a lot of trouble in this topic. Okay, we're almost done here. Glycine is a really interesting one. Short word is G. Glycine is just when you have a single hydrogen connected. So it's very small. The overall amino acid looks something like this, where we have the O-, the NH3 positive, and just a hydrogen, so we don't even draw it. It's very flexible, and sometimes it's considered polar just because of the polarity of the side chains, but at the end of the day, no glycine is the thing that just has a hydrogen, super flexible, and also it's the only amino acid that is achiral, and there's no chirality. We're not going to talk too much about chirality, but the fact that there are two hydrogens here means that there's no left and right-handed version of glycine. Almost done. 2 last ones to go that are very similar. So always try to group the glues and the asps together. Glutamine is GLN and asparagine is ASN. Now, this is where the one-letter codes can be quite challenging, so only memorize these if you need to. Glutamine is Q, and asparagine is N in the one-letter code. Now, glutamine and asparagine are both quite similar. The only difference is glutamine is a little bit longer. So what's going to happen is we're going to have one carbon out each end. For asparagine, the next carbon has an amide. For glutamine, we're going to put 2 extra carbons. So if you can count them, 1, 2, 1, 2, 3, it's just that glutamine is a little bit longer. The key thing with both of them is that the amides at the other end are polar. So they can do things like hydrogen bonding, but they're not going to ever change charge on you. So they're not ionizable. Putting it all together, again, take a screenshot of this if you'd like to have it all at once. You can see the charged amino acids here are cysteine, tyrosine, and histidine. These are the amino acids that are going to potentially change charge on you. So not only do you need to know their structure, but also their pKa. Wrapping up, we're almost done now. We just need to finish the charged side chains. So these ones also have pKa's, and you'll notice that they're going to always be charged at pH 7. Starting with lysine, the 3-letter code is LYS, the 1-letter code is K, and the structure is quite long. So here is our alpha carbon. We're going to have 1, 2, 3, 4 carbons, and then a nitrogen, NH3+. So the pKa of lysine is 10.5, which you'll remember, and this is an important thing to distinguish. Here, since we're dealing with nitrogen, the HA form is positive. The A form has no charge, right? The A form would be NH2. So the question is, at pH 7, what charge would this histidine be? Recall that when pH equals pKa, these two forms are equal. Since the pH is lower, that means that there must be a lot of hydrogen around. That means the HA form will dominate, and at pH 7, that means that we're always going to have a positive charge on lysine, similar to the N-terminus. So its key feature, again, is that it's long, but it's ionizable, and you can imagine that it's always positive. Of course, any pH above 10.5, you're going to start seeing neutral lysine, but that's pretty hard to do biologically. At pH 7, it's always positive. Lysine and arginine are the only positive amino acids in this camp. Arginine is a 3-letter code ARG. Its letter here is R. And if we go through, you'll see it's very similar to lysine with an interesting new functional group. So we're going to have 1, 2, 3 atoms to the nitrogen, but this nitrogen is then connected to another carbon, which is connected to NH2 and a double bonded N. So this is the neutral version, but if there's a second hydrogen here, that is the positive form. Again, the HA form with extra hydrogen is positive. The A form is neutral. The pKa of arginine is also around 10.5. What does that mean? Same as with lysine. I won't go through the whole steps again, but arginine, its key feature is that it's always positive, ionizable and positive. At pH 7, there's so much H around that this form dominates, right? The A form is just take away a hydrogen. Now you have the neutral form of arginine, but that's only going to exist above a pH of 10.5. Now, the last 2 amino acids here are the negative amino acids. These are amino acids that are always negative. So we have glutamate, and you'll keep in mind here that we had glutamine before. So as a quick reminder, glutamate and aspartate are going to be very similar to glutamine and asparagine. Here they ended in amides, 3 carbons and 2 carbons. Here, we're also going to do 3 carbons and 2 carbons, but the difference is we end with a carboxylic acid. These are the last ones. So glutamate is GLU, aspartate is ASP. Again, these 1-letter codes can be quite challenging. So glutamate is E, and aspartate, or aspartic acid, is D. Right? These are kind of acids. Now again, remember that at pH 7, we're never going to see them with those OHs. We're going to see negative charges. And that'll make sense when we see their relative pKa's. Right? For aspartic acid and glutamate, let's just say they're both 3, right? So let's think about that again. pH 7 for both of them. The pH is higher. That means that there's not as much hydrogen around. And so we have 2 forms to consider. The HA form is a carboxylic acid, and the A- form is oxygen with a negative charge. So if there's, oh my, that's kind of confusing, right? The pH is higher than the pKa, which means that there isn't very much hydrogen around. That means the A form is going to dominate. HA only favors if there's a lot of hydrogen around. That's why both glutamate and aspartate are typically negatively charged. With that in mind, we have the 4 charged amino acids. All of them are ionizable, and you need to know all of their pKa's. Now, with that done, and it's been quite a long video, I just want to cover one quick concept on mutations. In primary sequence is when we just look at the string of amino acids. So for example, if I have an N terminus, I could have alanine, leucine, and lysine, and glutamate, and cysteine, let's just say. Right, that's a string. We have the directionality. We're starting with alanine, going to cysteine. This is the protein primary sequence. Conservative substitutions are mutations where in a mutation, we're going to be changing the sequence. Conservative substitutions are where the change is minimal, right? We are changing the, so some sort of change in DNA sequence leads to a change in protein. If the change in DNA sequence doesn't lead to a change in the protein, we call that a silent mutation. Here, it's going to be conservative. For example, alanine turning into leucine, or isoleucine, or valine, right? If you recall, alanine was just a methyl group, and these were, similar, just carbons. They're a little bigger. They might have an effect, but they might be fairly similar, right? A critical substitution might be turning an alanine into a lysine, right? Alanine was just 1 carbon, but lysine is this very long chain, and it has a positive charge. That positive charge might be really bad for the protein's function, right? It's very different. So ideally, if you're thinking about mutations that can have an effect, when you're thinking about amino acids, it's good to think about those groups and what those key differences are. Again, if you don't have your amino acids memorized, this becomes very challenging. But alanine to things like this, we would expect minimal change. But critical substitutions where we have large changes, like alanine turning into lysine, or alternatively, lysine turning into alanine, right? Very big things turning into very small things could also have a big effect. So keep that in mind. But with that all said, we have covered all 20 amino acids and their pKa's. I wish you the best luck in committing these to memory. And in the next video, we'll be going into understanding the overall charge state of polypeptides as a whole. We'll really be watching or taking advantage of that video 3.2 material, talking about how we can use pH versus pKa to predict which form is dominant.